Hi, welcome back. We've seen now that a changing magnetic field creates a changing electric field, and a changing electric field creates a changing magnetic field. So what you have is kind of an oscillation where the change in magnetic field then produces the electric field, and then that electric field then changes the magnetic field, and then the series repeats. So this is an oscillation. Now, there's a specific type of oscillatory field called time-harmonic fields, which are very practical and are very important to us, and so that's what this video is on. A time-harmonic field is just a long way of saying that the field is periodic in time, so they repeat in time. And in this video we're going to look at, and in our course, we're going to look at sinusoidal fields. So of course, sinusoids repeat in time, so they are time harmonic fields. And the reason why we are interested in just sinusoids, it might seem kind of weird that, oh, why do I always have to be wondering about sinusoids all the time? Well, if you know Fourier analysis, then you know that other complicated waves, like squares or sawtooths or a mixture of the two or whatever, can be written as just a sum of a bunch of sinusoids. And all this is to say that we can extend what we're going to do here via Fourier's work to more complicated situations, but our course does not cover Fourier's work, so you have to learn that from some other course, like, for example, signals and systems. So just know from Fourier's work, we can extend our work on sinusoids to other types of fields. Okay, so we are going to conveniently analyze these time harmonic fields using the concepts of phasors, which you should already be familiar with, like from signals and systems or circuit analysis or differential equations. So recall that let's say that I have some number z and it's complex. So if that's the case, I can write it as e to the j phi, like this. And this phi is not related to cylindrical or spherical coordinates. This is just an angle phi. And so this is an exponential form of the written in the complex number. Or take the complex number, write it in exponential form. That's what this would be. Now, from Euler's relation or Euler's formula, Euler showed that this is equal to r times the cosine of that angle minus j, which is the imaginary unit, times r sine phi, right? So again, this should not be new to you. I'll suppose that this is not new. And we're going to let phi have a time dependence like that. We're going to call that omega t, and also just a constant theta. Okay, so that's not, again, that's we've seen omega before, but that's not w, that's omega, and this is theta. Theta is not related to the spherical coordinate theta. So now, if we do that, then r e to the j phi is equal to r e to the j omega t plus theta, like that. And we can separate out those dependencies, that time dependence right there, into r times e to the j omega t times e to the j theta, like that. So we've separated time, we factored time out like this. Now, how does this relate to time harmonic fields? We're getting there. Here it comes. So we can look at the real part of e to the j phi, right? So this is r e to the j phi, and the real part, according to Euler, the real part is r cosine phi. And so we can say that this is r cosine of phi, and phi we're saying is omega t plus theta. So you see, what we can do is we can write a time harmonic field like the cosine, certainly that's periodic in time, as being the real part of this complex number, this complex field. And similarly, the imaginary part of r to the j phi, according to Euler, by the way, that should be a plus sign, not a minus sign, plus sign, is equal to r sine. So there's nothing imaginary going on here. It's just it's a poor choice of name, I think, but we're using complex numbers or complex functions to represent sines and cosines, and the reason we do that will become clear in a few minutes. So now let's say we have a sinusoidal voltage, we'll call it V1, and maybe it's time harmonic, and again we're going to consider sines and cosines. So here's my time harmonic wave, v0 cosine omega t plus v, then or plus theta, then I can alternatively write this as the real part of v0 e to the j theta e to the j omega t, based on what we just said over here. You see, r is v0, and then we factor out the time dependence like that. So this might seem a little strange depending on how comfortable you are with complex numbers. But alternatively, a sine wave, we'll call it v0, we'll call it v2 of t, so we'll write v0 sine of omega t plus theta. We can represent this, or we can relate this to v1 of t with an additional phase angle of negative 90 degrees, right? The sine and cosine are out of phase by 90 degrees. Or we can write this as, and actually this turns out to be more convenient, we can write it as the imaginary part of v0 e to the j theta e to the j omega t. That convenience, you still might be doubting that it's more convenient. It is, and again, we're getting there. Now, if I drop the time dependence, so I'm just going to call, if I look at inside the brackets and I just look at this thing, I've dropped the time dependence. This is what we call a phasor. And in this case, since V0 is representing a voltage, we would call this the phasor voltage. Okay, and we are going to denote, we're going to make a lot of use out of these phasors, so we're going to give them their own notation, and we are going to say that this phasor, we're going to give it the notation V sub s. So the s, whenever you see that subscript, that means that we're talking about a phasor, and you see I've represented the phasor in exponential form, v0 e to the j theta. Alternatively, being that r is the magnitude, v0 is the magnitude, which we called r before, and theta is the angle, we can represent this in polar form. You might see this also, v0 angle theta. Again, because we've dropped the time dependence, we don't have the omega anywhere in there. So in general, a phasor can be a vector, or it can be a scalar, and it can depend on position, but it never depends on time, because that's the whole point. So here comes the convenient part. We've dropped the time dependence, which helps with convenience. So given a vector field, now let's say A, and so a vector field in general, as we saw earlier in the course, can be related to the spatial coordinates x, y, and z. And now we're saying we're dealing with time-dependent vector fields. So there's the time dependence. We can write, if it's a time-harmonic field, we can write this thing as this. A sub s, which is not dependent on time, we factor out the time dependence like this. So we can write any sort of time-harmonic field as the real part of this phasor times e to the j omega t. So let me give you an example. Let's say we had a vector field, which was a0, some amplitude, times cosine of omega t minus beta, where beta is a constant, x, maybe in the y direction like this. We can write that as the real part of a0 e to the minus j beta x, right? That's coming from the angle, right, in the y direction, and then factor out the time dependence. So this, all of this follows from what we've already said up here. So in this case, the phasor AS is a vector pointing in the y direction, and it is equal to a0 e to the minus j beta x ay. So that's my little example for you. Okay, now let's see what Maxwell has to say about this. How do Maxwell's equations change when our fields are time harmonic? So there are some derivatives via the del operator in Maxwell's equations. So let's investigate what happens to our vector fields, our time harmonic vector fields, that is, when we take the derivative with respect to time. So we'll suppose we still have that same A field. A is the phasor, is the real part of the phasor times the time dependence. Okay, now I can bring in the derivative operator into the brackets, and remember AS, the phasor is not dependent on time, and so I can bring not only the derivative operator inside the curly brackets, but I can bring it all the way to the e to the j omega t. And of course, when I take the derivative of e to the j omega t versus time, what I get is the j omega comes down in front, and I get this. So I get the same thing, right? But I just get multiplied by j omega, and so it's like this is the new phasor, right? I'll just speak loosely here and write this is the new a sub s, right? It's the old a sub s multiplied by j omega, and remember as is time independent. Okay, so we can conclude something from this very simple example, that when you take the derivative of a time harmonic field versus time, what you get is, in phasor domain, j omega times the old phasor. That's interesting. And similarly, you can show that when you integrate a time harmonic field over time, you get the old phasor divided by j omega. And so we can conclude that differentiation in time is multiplication by j omega in phasor domain, and integration in time is division by j omega in phasor domain. This, in differential equations class, is precisely why you learn about Fourier transforms and Laplace transforms. Laplace and Fourier are related to what we're doing here. They are in this phasor domain. I don't want to get too much into it, but they're in this phasor domain. And so in differential equations, what you did was, when you had a differential equation that you needed to solve, you took the transform. So instead of taking derivatives, once you transformed it into phasors, those derivatives turn out to be multiplying by j omega, or multiplying by s, right? You use s in Laplace. And integrals became 1 over s in the Laplace domain. So that converts the differential equation in time to an algebraic one in phasor domain. Anyway, let's go back to Maxwell's equations, and let's consider this guy here, that the curl of E is negative the time derivative of B, right? Remember that one? So now let's let E be the real part of some phasor times e to the j omega t. So all of this is to say, again, that might look goofy to you, but all we're saying here is we're letting E be a time harmonic field, i.e. a sinusoid or a cosine. And then let's say the same thing about B. So it is the real part of some phasor e to the j omega t. Then, if we make that assumption, then let's look at the curl of E. So this would be the curl of the real part of some phasor e to the j omega t. Okay, and we can, just like we said, we can bring this derivative operation essentially in. So this is the curl of the phasor now, e to the j omega t. So we're still just working with the left-hand side of this equation here. Now let's look at the right-hand side, the time derivative of B. So the time derivative, or the negative time derivative to be precise, is the negative time derivative of the real part of some phasor times e to the j omega t, right? And then we can bring in that derivative operation. And just like we said, we can bring the derivative operation all the way in past the phasor because the phasor is independent of time. And then the derivative of this thing is just that j omega comes down in front, right? Taking the derivative is like multiplying by j omega. So what we end up getting is negative the real part of the phasor, which is time independent, times j omega e to the j omega t, like that. So again, from Maxwell's equation here, we can compare this thing, which is the left-hand side of Maxwell's equation, with this thing, which is the right-hand side of Maxwell's equation, and we can conclude then, just by comparing, that the curl of the phasor of E is equal to minus j omega times the phasor of B. So the time dependence has dropped out since they're the same in both cases, and we don't have to, the real part can drop out, so we're left with negative j omega B is equal to the curl of E. And it's because that time dependence drops out that makes this kind of notation more convenient. So with phasors, phasors allow us to bring this time dependence in and put it, take it out as we please. We can just tack it on when we want to, and we can forget about it when we want to just work with the phasors. Okay, so this is one of Maxwell's equations when we have a time harmonic field, and again the S represents that we are dealing with these phasors with time harmonic fields. So let me just go ahead and write out, here's the point form of Maxwell's equations, right? So we'll just put the subscript S there. Like that. Here's the one we just derived. Nice. And then we didn't derive this one, but you can convince yourself, remember that taking the derivative is like multiplying by j omega. So this would be, Ampere's law there, down there. In integral form, remember that we can also write Maxwell's equations in integral form. We would have the following. This and Maxwell's law, or excuse me, Gauss's law for magnetism, like that. Okay, we have this. Faraday's law. And Ampere's law. S. So here the S is a surface. The integral is taken over a surface, and then the S subscripts here represent the phasor. Okay, so again, those are Maxwell's equations then when we're dealing with time-harmonic fields. So this can be a little tricky if you're not used to complex numbers and so forth, or complex functions. So let's work through a few examples coming up next. Thank you.